Hi everyone, my name is Rob Lyerly and I'm a research scientist at Meta. On behalf of all my co-authors, today I'll be presenting our paper, Skybridge, Bounded Staleness for Distributed Caches. Meta operates social media products like Facebook, Instagram, and WhatsApp used by billions of people around the world every day. Meta's products have strict latency and high availability requirements in order to provide a good user experience. In order to satisfy these requirements, Meta operates a loosely coupled serving stack located in multiple geographic regions worldwide. Here's an overview of Meta's geo-replicated serving stack. In this example, Alice sends a request to one of Meta's web servers to load her profile. The web server issues read requests to an in-memory caching layer called tau. Most requests hit and cache and are served immediately with low latency. On cache misses, the cache will first try to read the data from the local database replica and then fall back to the primary replica. Now, assume Bob wants to add Alice as a friend, which requires a write to the data store. Bob's request first goes to a web server, which then issues a write request to the cache. The cache proxies the write request to the primary database. While the write acknowledgement is returned to Bob, the system asynchronously replicates the write to other regions using a pub/sub service called Wormhole. Wormhole is responsible for updating other replicas such as databases and cache hosts. Wormhole has strict durability and ordering requirements. It can't lose data and it must publish events in order. Because of asynchronous replication, the system provides eventual consistency for users. There are no guarantees on when Alice's reads see Bob's writes. Eventual consistency hurts the user experience with Meta's products. In this example, Alice is an administrator of a private group. Alice is friends with Bob and adds him to the group. Alice's write flows to the database, adding him to the list of members that can access the group. The write is asynchronously propagated to other replicas. Bob then tries to load the group. However, Bob reads from a stale cache host that doesn't have the updated list of members. Bob can't access the group, leading to frustration with Meta's products. This begs the question, can we bound how long it takes writes to be visible while maintaining the scalability of eventual consistency? In essence, we want to provide a consistency semantic called bounded staleness for our users. In bounded staleness, a writer issues write W to the data store, which is committed at time t1. The system guarantees that any read R is able to observe W as long as it reaches the data store after the staleness bound has elapsed. This is guaranteed regardless of the region where the write or read occurred, or whether the read was served from a cache or database host. So why do we want to provide bounded staleness? First, bounded staleness is an intuitive semantic for users. Most users expect there's some delay in the system. What's surprising is when there's unbounded delay, leading to issues that persist indefinitely. Bounding this delay avoids these behaviors. Second, bounded staleness is scalable. It can be applied to all read requests since it gives the async replication stream time to achieve consistency. Other stronger forms of consistency require too much synchronization to be applied broadly at Meta's scale. Finally, bounded staleness applies to all writes, regardless of where the writes occur or who is doing them. Previously, we implemented a system called Flight Tracker that provides read your writes consistency. Read your writes is a powerful semantic for users, but it only makes guarantees about that particular user's writes. It makes no guarantees about anybody else's. Bounded staleness pairs well with read your writes. You're able to see your writes immediately and everybody else's writes after a short delay. So what are the challenges in providing bounded staleness? On average, the async replication stream is able to propagate updates to all replicas within a couple of seconds. However, there are many sources of replication lag due to the replication stream's strict durability and ordering requirements. These properties lead to head-of-line blocking in the system. For example, if there's a network partition or a host crashes, writes back up and the replication stream lags until the end-to-end pipeline becomes healthy again. So how can we solve this problem? At a high level, the cache can try to compensate for replication lag. Internally, cache hosts track the replication progress. If replication lag is larger than the staleness bound, then the cache is considered stale. To enforce bounded staleness on requests where replication is lagging, cache hosts can refill their cache using a more up-to-date source, such as the database primary. While this ensures clients see bounded staleness, it can cause significant operational issues. First, it's not fine-grained. Cache hosts track replication progress per database shard. If that shard's replication stream starts lagging, the entire shard is considered stale and all read requests for that shard trigger refills. This can cause thundering herds on the database primary, triggering further replication lag. Second, it's wasteful. Meta's workload is read-heavy, meaning that most data on the shard doesn't change frequently. In this simple implementation, almost all of the bounded staleness cache misses are false positives. Only a small fraction of cache misses are for truly stale data. What would make this solution scalable is if cache hosts had a staleness oracle that could tell them exactly which cache items are stale when replication is lagging. Cache hosts could consult the oracle on read requests to figure out exactly which cache items are up to date and which need to be refilled, including versioning information required to satisfy bounded staleness. This is Skybridge's key capability. Skybridge provides fine-grained staleness information to enforce bounded staleness. To achieve this functionality, Skybridge must index metadata about all writes committed to all database shards. Here's an overview of how Skybridge operates. On write requests, cache hosts issue writes to the database. The write is sent through the async replication pipeline as normal. Additionally, cache hosts coordinate with several other services as part of handling writes. First, they open leases on the database shards that they want to write to. Skybridge uses leases to track who is writing to which shards and determine its data completeness. More on that in a second. After the write is committed, cache hosts send metadata about the write to Skybridge. Skybridge batches write metadata collected from local cache hosts and replicates it to Skybridge deployments in other regions. There, hosts index the metadata and make it available for querying from cache hosts. Skybridge assists cache hosts in identifying stale cache items, eliminating the need to spuriously refill cache from other sources. At a high level, Skybridge seems similar to the existing async replication stream. This begs the question, how does Skybridge avoid the same sources of replication lag? Skybridge implements a novel replication semantic called replication with gap detection. In essence, Skybridge relaxes the strict guarantees provided by the existing replication stream. Skybridge can do this precisely because of the presence of the existing replication stream, which takes care of durability and ordering. This allows Skybridge to focus on real-time replication. Skybridge's replication stream utilizes three properties to avoid replication lag. It only replicates write metadata, it allows known data loss, and it utilizes out-of-order replication. Let's talk about each of these in turn. The first property is that Skybridge only replicates write metadata. The main replication stream needs to ingest everything about the database commit, including versioning information, key, and changed data. Skybridge, on the other hand, only needs to ingest the write metadata, i.e. version and key. This is because Skybridge is only responsible for identifying which cache items are stale. It is not responsible for filling cache. The cache hosts themselves are responsible for filling cache when Skybridge identifies stale entries. Focusing only on replicating write metadata leads to significant CPU, memory, and network bandwidth savings in Skybridge's replication stream. Second, Skybridge allows known data loss. The regular replication stream is not allowed to lose data. Because of this, it uses complex and heavyweight protocols like distributed consensus to ensure that data is durably replicated. Skybridge, on the other hand, is allowed to lose data. Recall the interaction with cache hosts on the read path, where cache hosts ask if a particular data item is stale. If Skybridge has data loss, it can return an indeterminate result to cache hosts. The cache hosts can then conservatively refill cache to enforce bounded staleness. Because Skybridge doesn't require complete data, it will just skip over gaps in the replication stream in order to focus on the most recent writes. The key is that to take advantage of this fallback while still enforcing bounded staleness, Skybridge must be able to detect when it has lost data. This is where Skylease comes into play. Skybridge uses leases open with Skylease to detect when hosts didn't send information about committed writes. For more details, see the paper. Finally, Skybridge's replication stream allows out-of-order replication. The right metadata in Skybridge's replication stream is a form of conflict-free replicated data type. At a high level, this means that Skybridge's data can be delivered in any order, and Skybridge's indexes will converge to the same state. Skybridge uses out-of-order replication to work around transient issues like network congestion and late data delivery from cache hosts. Rather than waiting for issues to resolve, Skybridge continues sending whatever data it has to focus on the tail of recent writes. In the meantime, Skybridge compensates by reporting data loss to cache hosts. Whenever data does get delivered, Skybridge will make it available for querying. With these three properties, Skybridge, cache hosts, and the existing replication stream together provide boundless staleness for billions of read requests per second. Now let's talk about a few implementation details. While Skybridge's goal is to provide boundless staleness on every single read request, it cannot regress cache availability or latency. Doing so would risk harming the health of Meta's serving stack. We struck a practical balance between enforcing consistency without harming system health. By default, Skybridge provides best effort boundless staleness on read requests. Cache hosts will rate limit boundless staleness refills if there are too many cache items that can't be proven up to date locally. There's also an opt-in fail-close mode where users are either guaranteed to get boundless staleness or the cache returns an error. This is for users that require stricter consistency for correctness. By default, Skybridge targets 2-second boundless staleness. This is a good balance between what's achievable given Meta's geo-replicated serving stack and is also a practical human scale bound for users. This bound is tunable, however. It represents a trade-off between cost and consistency. Tighter bounds mean more synchronization through refills. Let's move on to an evaluation of Skybridge. We evaluated Skybridge on Meta's production workload. We built a staleness checking service, which we called the checker. The checker samples writes from cache hosts, sleeps for 2 seconds from the database commit timestamp, then issues read requests to check boundless staleness. The checker issues 3 types of read requests. No boundless staleness requests explicitly disable boundless staleness protections. This is equivalent to what users would get without Skybridge. Best effort requests use the default protections provided by Skybridge. Cache hosts try to enforce boundless staleness, but rate limit the refill path. Finally, fail-close requests either guarantee consistency or return an error. We captured a trace of checker traffic over a 7-day period. Here, we see 2-second cache consistency as measured by the checker. While staleness fluctuates throughout the day, we see that by using Skybridge, consistency greatly improves. Without Skybridge, cache only provides about 4 nines of consistency. In best effort mode, consistency improves to 5 nines. In fail-close mode, it jumps to almost 7 nines. This is multiple orders of magnitude better than what caches provide by default. For best effort reads, the biggest reason for staleness is long shard lag. Skybridge is an in-memory service and has limited retention. If lag exceeds Skybridge's retention, it reports indeterminate results. This happens frequently enough to hit the refill rate limits. We also dug into why there's any staleness with fail-closed reads. It turns out that clock skew and other checker implementation details are a factor at this level. Next, we wanted to evaluate Skybridge's efficiency in proving cache items up to date without requiring cache refills. We measured what percentage of read requests were able to be proven up to date using the replication stream's internal progress tracker, Skybridge Bloom filters, an optimization where Skybridge hosts proactively stream metadata to cache hosts, and local requests to the in-region Skybridge. We see that approximately 3 nines of read requests are proven up to date using the replication tracker. However, by utilizing Skybridge's capabilities, approximately 5 nines of requests are able to be proven up to date without refilling caches. This shows how fine-grained staleness information filters out a significant amount of spurious fill requests when enforcing boundless staleness. Skybridge is able to achieve this while being very lightweight. Skybridge's server footprint is only 0.54% the size of the existing cache deployment, and Skybridge requires only 2.7% as much bandwidth as the existing replication stream. Skybridge is lightweight and adds minimal resources to the existing serving stack. So in conclusion, Skybridge provides fine-grained information about which cache items are stale for cache hosts. Skybridge is effective, helping boost 2-second cache consistency to almost 7 nines. Finally, Skybridge is lightweight, enabling cache hosts to apply bounded staleness to billions of read requests per second while only requiring a small amount of resources. Thank you.